Welcome back to another video. So last time we did problem 2 of Project Euler where we went over the Fibonacci series problem. This time we're going to go over problem 3. Let's look at the question then. The prime numbers, the prime factors of 13195 are 5, 7, 13, and 29. What is the largest prime factor of the number, this big number? So let's try to understand what the problem is. So prime numbers are numbers which are only divisible by 1 and itself. So if you look at 5, you cannot divide 5 by any whole number. Uh, so it will only be divisible by 1 and itself. Similarly with 7, 13, and 29. And 13195 is divisible by these prime numbers. So the largest prime number in this case for 13195 is 29. And we're looking for the largest prime factor of this huge number. So if we were to find out all the prime numbers which can divide this number, we want the largest number out of those, and that is our answer. So this is a pretty like a tricky question because it it's easy to find prime numbers, but it's difficult to find them efficiently. So we can effectively run a loop, a bunch of nested loops, and figure out what the prime number of a given number is, like a prime factor of a given number is. But finding it efficiently is could require a bit of thinking. So let's think about this. So if we go over our problem and we just create another case in this switch case, and let's just call this prime factor and create a function for prime factor, which will also take an input and give out an int. So what we will be doing, the input in our case will be 13195 or this big number. So the most naive way of doing this would be looping through 2 and uh, all the way to the input and incrementing and then seeing if I is in if I is, let's say, a prime number, and we will be creating this function. So we will be creating this function for figuring out if a number is a prime number, uh, which will take an input int, and it will give out a Boolean, which will be either be like is prime. If it's a prime, then it will return a true, or it will return a false. Uh, so if it's a prime, then we can keep track of uh, a max prime here. Uh, and so initially the maximum prime could be 2, uh, or it can be, let's say, 1. Uh, 1 is not essentially a prime number, but I don't know, it's debatable. Uh, but we can have 1 as the initial number, and then we assign the max number whenever it's a prime. So let's go over this again. Yeah. So we're looping through all the numbers from 2 to the input. If the number is a prime number, then we keep track of that prime number. This is the most naive way of doing this. And in order to figure out if the number is a prime number, what we do is uh, we start from 2. So it'll be like I is 2, I less than equals the input, I plus plus. If input divisible by I, then we just return false. And at the end, we just return true. So this will figure out if the number is a prime number or not. So given an input, let's say the input is 5, then we start from 2 and all the way to 5. I mean, I think this would be the right way. So from 2 to 4, we try to divide 5 by the I. And since it will not be divisible by 5 anywhere, it will just get out of this loop and return true. And it will be the right thing. Like it is not a prime, it is a prime number. And if we were to give it something like 6, then immediately it will be divisible by 2 and it will return a false, saying that it's not a prime number. So this is one way of solving this problem, like going over everything. So essentially what we're doing is this is uh, this is one loop and inside it we're having another loop. So we are having a nested loop here, which is not very efficient. So one way to solve this would be like have the max prime as whatever number, and we can start from the input and all the way. Uh, let's just try out this function for now, and then we can move on to making it more efficient. So we can have the problem as 3. Input would be 13195. Right, so we need to start from 2, not there was a typo there. So if it's a prime, and I forgot one more case here. If it's a prime and if the input is divisible by the number, so let's look at it one more time. Max prime, we set it initially to some small number. We loop from 2 to the input, uh, and I don't think we need to go actually to the input. So while it's less than the input and we increment it, if the input is divisible by the number and if it's a prime number, then the max prime we set it to I. And the way we are figuring out if a number is a prime number is we loop from 2 up to the input and we try to divide it by that number. And if it's divisible, then we return false or we return true. So if we try to run that with the input, we get 29, which is what we were looking for. So this works, but it's not very efficient because we're looping through we're looping through 2 to the number, and then in each loop, we're looping again from 2 to the number, so 2 to the current I. So it would be an O of n squared since we are having a nested loop. Uh, so we can make this a little bit better by starting from the input, and while it's starting from input minus 1, and or you could just start from the input. Yeah, that should be okay. What if the input itself is prime, uh, and we go till while it's greater than 1, and we decrement at each step, and we don't need to have that. And as soon as we hit a prime number, we just return that prime number, or we just return 0. Um, yeah, because this should give us whatever the prime number we want. It should probably never hit this case because we're starting from the input, we're going up to 1. So maybe we should return 1 here. Uh, and we are decrementing. And if the input is divisible by I and it's a prime number, then we just return it immediately because we don't need to keep track of the max prime here. We in this case we are breaking as soon as we hit a prime number, uh, and that will be our max prime. So if we look at that, we still get the same answer. Oh yeah, I think we can also write our tests for this, but yeah, we can do that at the end. Uh, so this is a little bit better, but even here, the worst case time complexity is still O of n squared. So the way to make this better would be if you think about it, if you think about prime numbers, prime factors, or factors in general, then let's take an example of 36. So over here we're looping from 2, 3, 4, 5, 6 all the way, uh, all the way to 35. And we don't need to do this. Like 36 is never going to be divisible by 35 or 34 or 33 all the way to uh, some number, right? We don't need to go all the way to there. Maybe if you think about it, if we go till 18, it's never going to be divisible by 19. Like that will never happen. 18, it can happen because 18 times 2 would give us 36. So we don't need to go past the given input divided by 2. Like this will be our the max number which can divide the given input, which makes sense. Like we don't need to go all the way from input to 2. We can maybe start at input divided by 2. But now, if you think about it, uh, we don't even have to go till 18 because 18 is clearly like it's going to be divisible by 2. If a given number is divisible by 2, then we can run a loop of sorts which will check if the resultant number is also divisible by 2, and we can divide it again. So in that case, we can come to like what's in that case we can come to 9. And now we have halved our loop. Like we don't need to run our loop from 18 to 2. Instead, we will be running our loop from 9 to 2. So what I'm getting at is while the number, so let's say we store the number in an input, or we just use x as our previous example. So we're storing this in x. So while x is divisible by 2, what we can do is divide x by 2. So while it's even, we just divide it by 2. And now we have reached 9. And now we only need to check with all odd numbers from 3 to 9, uh, by if it's divisible by anything, or from 9 to 3 if it's divisible by something, and if that's a prime, then that's our max prime. And this is a way to optimize our current solution. So this would be our loop. So this checks if at the end of this loop, we know that whatever we have is an odd number. And now what we need to do is, since we are using x now, uh, we have to loop from x to 3, or while it's greater than 2. And we decrement by 2 at every step because we no longer need even numbers because we have already checked that. We have already gone through this loop, and we now know that whatever we have at the end of this, it'll not be even. So now we only check with odd numbers, and so we need to go through that. Like if I is an even number, then we just skip, right? We do a continue here, and so let's think about this a little more. So now we are only going through odd numbers. If I is even, then we just continue. Uh, and yeah, now we can go through this loop. So if we try to do this again, okay, this is the problem. So I'll just comment this out. Yeah, see, now we get the same answer, but this is a lot more efficient than what we had earlier because we have eliminated all the unnecessary steps that we are going through in order to find the factor. Now we're directly going to the point and figuring out if the factors are prime or not. And as soon as we have the max prime, we're just returning it back. And we can even make this a little more efficient by because if we think about this, uh, 9 will still be three will still be a factor of nine. So we don't even have to start our loop from nine. We can start our loop from uh, and from three because uh, like whatever the square root of our current number is, that's where we can start. So if you think about, like, let's say we have 36, then the square root of 36 would be 6. And what are the factors we have for 36? We can have 1, 2, 3, 4, 6, and now we're coming back. So we have 6, we have 8, we have 12, and here would be 18, and here would be 36. So whatever the input number we are getting, after we reach the square root of that number, we are repeating. Like we don't need to check this whole loop because whatever the prime factor would be in this list. So coming back to our code, what we can do over here is we can like do something like the square root uh, of x. So we start from the square root of x and up until we reach 2, because this will not ever happen. We are already dividing everything by 2. Uh, and that's how we can run our loop. So we can do something like mat dot square of x, and from there our function will run. Uh, yeah, we'll need to convert this into an integer because it can be a floating point number. Let's see what's wrong here. Also, I think what we will need to do is float 64 our x, get a square root, get an integer, and that will be our starting point. So now if we run our function again, we still get our answer, but this is probably the uh, a, a lot more efficient than what we had earlier. And of course, in the worst case, this is still order of n. Oh no, this shouldn't be order of n squared in the worst case because let's say that the input itself is a prime number. And I was thinking it that way, like uh, if we start from the number itself, but we're not starting from the number itself, we're starting from the square root of the number. So this would decrease our complexity to square root of n times n. This would be our time complexity of this solution in the worst case. Like in the best case, this is probably like a lot more faster because we're breaking as soon as we hit a prime number and we return it back. But still, in the worst case, it will still be this. Let's say the input is 5. So we're not going to go into this loop because it's not going to be divisible by 2. We're going to start from the square root of 5, which would be something like 2. So we wouldn't get into this, but let's say that if it's a larger number like, I don't know, 31. So we would get into the square root, which would be like 5 point something. So it would pick it up as like 5 or 6. So we start from that, we we get into the loop, and we find out if each number is a prime number. And this would be the n and the square root of n times the n. That's our time complexity. So cool. This was a fun exercise of making it more efficient. Now let's try it with the initial problem that we got. So to copy it over, I'll just do this. This is the answer that we're looking for. Let's try it out. Yep, that's the right answer. So we can like add the tests for this problem now. Uh, what's the problem? I'll have to, yeah, we can just copy this over there now. And our initial problem was this, and we were expecting 29. And our next problem was this, and we're expecting this. And our function is prime factors. Now, if we run make test, the test should pass all of them. Awesome. We're missing some test coverage. I think the stuff that we're missing is in the problem function. So yeah, this we haven't tested this function out, so that's why it's giving us a lower test test coverage report. So anyway, that's our problem 3 of Project Euler. Thanks for watching, and I'll see you in the next video.